In a groundbreaking finding, astronomers have finally discovered the gravitational wave background, the big hum of the cosmos. This discovery shows us that the universe is constantly humming with a frequency of a billionth of a hertz. The gravitational wave background could result from colliding supermassive black holes that was earlier thought to be an impossible phenomenon due to the final parsec problem. These gravitational waves stretch light years across and have frequencies in the range of nanohertz, showing how challenging it is to detect them. Just like the discovery of the cosmic microwave background almost 60 years ago, this discovery has opened doors to new physics. So what exactly is gravitational wave background? Why did astronomers think that supermassive black holes could not merge to produce this hum? Finally, and most importantly, how is it going to revolutionize our understanding of the cosmos? At the core of almost every galaxy resides a supermassive black hole, which co-evolves with its host galaxy. These black holes are incredibly massive, ranging from hundreds of thousands to billions of times the mass of our Sun. A galaxy and its supermassive black hole grow under the influence of each other. Initially, astronomers believed that galaxies were isolated structures that did not interact with each other. But as astronomers built more powerful telescopes, they started observing galaxies that were not only simply interacting, but also merging with each other. With this observation, they naturally became curious about the fate of the black holes at the heart of these merging galaxies. What happens to these black holes when their host galaxies come together? Do they merge as well? The most straightforward explanation for the fate of supermassive black holes during galaxy mergers is their eventual merger into a single black hole. This occurs when two supermassive black holes come close to each other and enter a tight orbit. As they continue to approach one another due to the gravitational interactions, they release gravitational waves, which dissipate their orbital energy. This causes their orbits to gradually shrink, bringing them closer together. However, the math doesn't allow that. There is a challenge known as the final parsec problem in astrophysics. According to this problem, their orbits cannot become smaller than 1 parsec, or approximately 3 light years. At such close separations, the black holes would have expelled all surrounding stars, leaving them with no means to exchange energy. Consequently, there is no other astrophysical process that can further reduce the separation between the supermassive black holes. As a result, supermassive black holes are believed to remain in close proximity without merging for significant periods of time. Now, you must be thinking that LIGO recently detected gravitational waves from black hole mergers. So why didn't the final parsec problem come into the picture in that case? Well, the gravitational waves detected by LIGO were from merging stellar mass black holes that result from the death of massive stars. These black holes are small, having masses ranging from 5 to a few tens of solar masses. But the story is different in the case of supermassive black holes. When supermassive black holes reach a separation distance of 1 parsec, it becomes difficult for them to lose their orbital energy. However, if a mechanism exists that can help them overcome this difficulty and bring them closer than 1 parsec, these supermassive black hole binaries would spiral around each other, emitting gravitational waves in the nanohertz frequency range. Given the common occurrence of galaxy mergers, it is expected that there are numerous such spiraling binaries of supermassive black holes. Detecting gravitational waves with nanohertz frequencies is quite difficult. The accuracy required for such detections was not achievable with existing telescopes. So astronomers found a solution by utilizing pulsars, which are dead stars, as messengers of gravitational waves. And the way it was done is going to blow your mind. Pulsars are remarkable celestial objects. They are highly magnetized pulsating neutron stars that emit beams of energetic particles along their magnetic axes. This results in regular pulses of emission when the magnetic axis aligns with our line of sight. The pulses emitted by these cosmic lighthouses fall into the radio frequency range and can be detected by sensitive radio telescopes. Pulsars rotate rapidly, with spin rates ranging from a few to 1,000 times per second, making their periods incredibly precise. The period of these radio pulses is so accurate that astronomers use them as cosmic clocks for precise timing measurements. They barely miss a beat. Gravitational waves, on the other hand, are ripples in space-time, akin to ripples spreading on the surface of a still pond after a stone is dropped. As gravitational waves traverse the universe, they cause compression and expansion of space-time. This unique property allows us to detect them. When observing a pulsar, the presence of gravitational waves can cause the space-time to become distorted, altering the arrival time of the pulses. As the distance covered by the radio pulses changes, the timing delay can provide valuable information about the direction from which the gravitational waves originate, provided the pulsar's location in the sky is accurately known. Now, in order to understand what exactly led astronomers to detect the gravitational wave background, there's just one important diagram you should know about: the Hellings and Downs curve. It's a relationship between the angular separation between a pair of pulsars in the sky and correlation between the delayed timings of such pairs. Simply put, if you take any pair of pulsars in your array and there's a gravitational wave that has passed between them, then the delay of the pulses caused by that wave must be correlated to the angular distance between the two pairs in the sky. So when we examine the timing data of multiple pairs of pulsars and analyze the relationship between them, a distinctive pattern called the Hellings-Downs curve emerges. This curve represents the influence of gravitational waves on pulsars from various directions. If you look closely, you'll notice that there's a dip in the curve when the angle reaches about 60 degrees. The dip occurs because pulsars at this specific angular separation experience distinct portions of the gravitational wave pattern, resulting in a decrease in their correlation. When pulsars are closer together or farther apart, they tend to be affected by similar gravitational wave effects, leading to stronger correlations between their signals. Now, the only task left was to detect this relationship among the pulsars observed in radio wavelengths. And this marks the entry of nanograv. The North American Nanohertz Observatory for Gravitational Waves, or nanograv, is an international collaboration of some of the most sensitive radio telescopes. They include the Green Bank Telescope, the Arecibo Telescope, and the Very Large Array working with nature's most stable clocks, the pulsars. Scientists from nanograv embarked on a groundbreaking study using an array of 67 millisecond pulsars to investigate the presence of gravitational waves. The Indian, Parkes, and European pulsar timing arrays also contributed to the study. It allowed them to create a galaxy-sized detector using these cosmic lighthouses. The teams watched the pulsars for 15 years to see if they followed the Hellings-Downs curve. And to their surprise, it did. This signified the presence of gravitational waves of nanohertz frequency. But how do we know that the waves are isotropic? In simple terms, how can we confirm that they are coming from all directions in the sky? The answer to this question lies in the graph of signal-to-noise ratio over time with an increasing number of pulsars. As the number of pulsars increased, the signal-to-noise ratio also increased, indicating a greater abundance of observed signals. This significant trend confirmed that gravitational waves were indeed reaching us from various regions across the universe, and not just from one direction. The amplitude of the signal in the nanohertz frequency matched the gravitational waves generated by several supermassive black hole binaries, not just from a single binary system. This is the astrophysical explanation. But astronomers also explored alternative cosmological scenarios, including events during the early stages of the universe. the presence of cosmic strings, and cosmic inflation. However, the analysis of these scenarios did not yield definitive results, leaving the supermassive black hole binaries as the most plausible explanation. If indeed the observed gravitational waves were generated by supermassive black hole binaries, it suggests that such binary systems are not uncommon in the universe. This finding challenges the notion that the formation of close binary systems of supermassive black holes beyond a distance of 1 parsec is rare or restricted. The study's results provide a potential solution to the long-standing final parsec problem, demonstrating that these binary systems can overcome the difficulty of orbital energy loss and continue spiraling closer to each other. Astronomers now aim to integrate more pulsar timing arrays into their network to understand the gravitational wave background better. This low-frequency signal could hold answers to some of the deepest mysteries in astronomy. Recently, astronomers spotted the largest explosion in the universe so far. It's so energetic that no physics phenomenon has been able to explain it yet. It's something that has never been seen in the universe before. If you missed this episode, be sure to catch up on this exciting discovery.